All right. It seems like just yesterday that we were here. So anyway, today we're going to start chapter 9. Yesterday was a review session from Stats 1, and when you see Stats chapter 9, you'll see why it was so important to review those particular concepts. So I've got chapter 9 open right here, and this is our first look at hypothesis testing. And hypothesis testing is a procedure that is designed to help us draw conclusions about the properties of some data set or other, given that we typically do not have access to an entire population of data. What we often end up doing is using a sample of data and using whatever's in that sample to draw conclusions about the underlying population. So this can be done in several different ways, but one of the more popular ways is this method of hypothesis testing, and we can see it'll be used over and over and over again throughout the entire course, and because it's so useful and so important. So primarily, we're going to focus our attention on, at least in this chapter, drawing conclusions about the population mean and the population proportion. Later on, that will change, but right now, we'll be focusing just on those two things, the mean and the proportion. By the way, the reason for that is because the other testing that we'll be doing will require us to use a different probability distribution, ones that we don't actually know yet. They will be introduced later on as we need them. Right now, more or less, the most important distributions that we know, at least the continuous ones, are the t and the standard normal, and that's great. And they're fantastic for a lot of applications, but sooner or later we'll find other applications where they're not what we need, and then we'll introduce other distributions. Okay, but not tonight. Okay, so anyway, you can see there's a lot of concepts that we'll be looking at. So now this is a formal procedure. So in the beginning, it's going to seem very strange and abstract, but once we tie it all together with actual examples, I think you'll realize it's not too difficult. It's just that it does take some getting used to. So there's always going to be two hypotheses in each hypothesis test. So let me start by noting these in my notes, which, by the way, I think I mentioned it in my email this morning. After each session, what I will be doing is posting in Blackboard the handwritten notes from the night before. Since last night we were reviewing, you'll find them in the folder labeled review, along with the actual slides. And also there's a PDF here. I usually try to do at least one PDF to go along with whatever other format we're using, because sometimes when you switch back and forth between the Mac and the PC, it can cause issues with symbols and equations and that type of thing. So if you see them both in there and you're wondering why, it's because I want to make sure that one of them is legible no matter what computer you're using. These are the notes. And just a quick reminder, this is all the stuff we did last night. There it is. So yeah, you can see this is what we were doing. And so I'll just continue to post these on Blackboard as we go along. So even if for some reason you can't be here, you can at least read through those handwritten notes and the slides that are provided by the book, as well as the video, which is up here somewhere. Yeah, these are going to have their own folder, because I find that if they don't, it gets very confusing where to find them. And you could tell it's this one because it's got the MP4 extension. And so, if you were here last night, you don't have to watch the video if you don't want to. But if you weren't, it might be a good idea to at least go skim through it and see what we were doing. Okay, anyway, having said all that, let's get back to the new material. What's going on here? There we go. So there's two hypotheses that we have to specify for every test that we carry out. Okay. So the first one is called the null hypothesis. And by the way, if you're not that familiar with it, the word null is often used in British English to represent zero or nothing. So this hypothesis is written H with a little zero subscript. And what does it represent? Think of this as a statement that is assumed to be true unless we find strong, the keyword there is strong, contradictory evidence against it. Okay, so in other words, this is what we're starting out assuming. And if we find evidence to suggest otherwise, we will reject this hypothesis in favor of what's called the alternative hypothesis. And that will be written with H subscript A, although I do want to point out not every single book does it exactly the same way. HA. And so what's happening here is that you can think of this as this is a statement that will be accepted in place of the null hypothesis if it is rejected. Okay, in other words, if we find evidence to show that the null is not correct, then we will accept in its place the alternative hypothesis. So we have to set this up carefully to make sure that the null and the alternative cover every possibility. Okay, it's either one or the other. One of them must be true. The question is which one. So then let's see. Well, okay. So like here they're giving a simple example. Suppose suppose we have some new method that we are bringing out to market and we think that it's better than the existing one. Or maybe it's a new textbook, let's say, and we think it's better than the existing one. Well, we can't assume anything here. So we'll assume in the beginning that the new book is no better than the old one, unless we have evidence that it's better, and then we can reject the null and accept the alternative. Yeah, so they're all more or less the same thing. Like especially in medicine, you can see why this is so important. Suppose a new drug is released and the company claims, yeah, don't worry, it'll lower your blood pressure. Well, when it's tested, which takes a long time, of course, we can't assume that it works. What we have to do instead is the burden of proof is on the company to show that it does work. So we'll assume that it doesn't unless they can show us proof that it does work. And so the null is that the drug is no better than the existing drugs in lowering blood pressure. The alternative is that it is better, but that requires hard evidence. Okay. So now here we're not going to be testing anything about, drugs or anything like that. We're going to be testing hypotheses about the values of the population mean. For example, what if we're trying to find out if the average age of all the people in the United States is over 30 or something along those lines? That's the kind of thing we'll be doing here. Or what if a company wants to know if the average salary is over $100,000? Those are the kinds of tests that we can do here. Now, here's one. Suppose that we are concerned that, let's say this is Coca-Cola and they're selling bottles of soda, 67.6 fluid ounces, which is, I guess, about 2 liters. And yeah, that sounds about right. The thing is, according to the setup, if the bottles are just a little bit over full, it's not really a problem. But if they're under full, there's not quite enough soda in there. That's a problem because then we could get into trouble with the FDA. So what we need to do is test the bottles and assume or try to find out if they are underfilled. Just like this. we're not going to, if we find that the bottles are underfilled, let's say we'll make a major change to the production process, which would be very costly. So we don't want to do that unless we have proof that it's absolutely necessary. So what's going to happen here is that the null will be that we do actually have at least 67.7, 7.6 ounces of soda. The alternative will be that it does not, that it's too low. And that way, if we do reject the null hypothesis, it'll only be because we have very strong evidence that the bottles are underfilled. And then that means we better do something about it, no matter how expensive it is. So that's why it's set up this way. We don't want to jump to the wrong conclusion about this. We don't want to recall all the bottles unless we have evidence that it's necessary. So you can see what's going to happen here with these problems. The challenge will always be setting up the null and the alternative hypotheses correctly. That is easy to get wrong. Okay, so we have to think about what are we trying to prove or disprove. Here we're trying to prove, I guess what we should say is we're trying to disprove that the bottles are full or filled correctly. And so the alternative hypothesis can be thought of as what is it that we're trying to disprove? Okay, so now as far as means are concerned, here's the way we're going to write this. This is a very abstract way of putting these same hypotheses. And also, if you notice, there's three different ways in which they can be written. So let's take a look at these. So we're going to, by the way, we're going to use this notation. The little zero means this is the hypothesized value of mu. We don't know what it is. I mean, obviously, if we knew what the population mean was, none of this would be necessary. So when we don't have actual numbers, this is what we'll do instead. So mu with a zero is the hypothesized value. Now, we can structure our hypothesis test in three different ways. We can construct what's called a right-tailed test, which means, oh, by the way, this is something I run into all the time. They call it an upper tail test. I like to think of it as a right tail test. So I'm probably going to accidentally call it that every time. So be aware that what the book is saying right tail test, I will almost certainly call it or what they're calling an upper tail test. I'm going to call it a right tail test just because that's what I'm used to. And so it means that you're looking at in this case, the normal distribution at what's happening up here somewhere. Okay, depending on the situation that you're in. So the right tail test is written in the following way. The null and the alternative are set up in such a way that the alternative will be mu is greater than or equal to the specified value. Okay, so you can see it's right here. Oh, whoops, sorry. I did this incorrectly. This should be strictly right, greater than. Hold on. Well, it has to include everything else. It'll look like this. So now they really do cover all the possibilities. Now, this is a case where you would set it up if there's some really important reason why you need to know if the mean is too high or higher than mu zero. The hypothesized amount. All right. So in other words, we're looking for evidence. So let's say that see, I'm trying to think of a good example off the top of my head. A situation where having too much is worse than not enough. So, well, all right, maybe we'll come back to that one. But this is a scenario where it's critically important to find out right away if the mean is higher than we realize. So it's a right-tailed test. And the reason why it's right-tailed is because if you notice this greater than sign is pointing to the right, okay? That's one way of looking at it. Okay. Um, or, it could be something as simple as this. Um, suppose that um, a shipping company like FedEx has found that overfilled packages are at risk of exploding or something along those lines. Okay. In other words, a box that says 1 pound has 1 pound and 3 ounces in it. There's no such risk if they're underfilled. Okay. Then they're fine. They won't have a problem. So that means FedEx needs to find out if this is a problem. And if it is, changes will be made right away. This is too important. Okay. But if we don't have enough evidence to suggest that, then we're not going to do anything because it would be horribly expensive to change the way we package our whatever comes in. So that would be an example of a right-tailed test because we are looking for strong evidence that the packages are overfilled. Okay. Of course, with packages, it's not like you're not selling a product in a store. When they send you packages, I don't know how they decide how much to put in each box, but we're assuming here that overfilling the boxes is a big problem. Underfilling them just means they have to use more boxes. So in their judgment, overfilled is worse than underfilled. Now, the second possibility, as you can probably guess, is the left-tail test. Okay. And the only thing we have to change is the direction of the inequalities. And remember too, this is sometimes called the lower tail test. So, of course, the word tail will refer to the, at least in this chapter, or the normal or the t distribution. Looking at this area down here. And so the null and the alternative are set up in the following way. So the alternative rather, is the one we're looking for evidence of. Null is everything else. So basically what you should probably do when you set up these tests is choose the alternative first. I think you'll find that it's easier that way. And so here's a case where, let's say, that a coffee company has been accused by the FDA of selling bags of coffee beans that contain less coffee than the label says on the package. Okay, in other words, it says 16 ounces, but it's really only 15.2 ounces. The company has got to make sure this is not the case because otherwise they're going to get in all kinds of trouble because they're basically ripping off the consumers. And they could be heavily fined if that turns out to be true. So now it could be that they're not doing this on purpose. Maybe the manufacturing process has something that's going wrong, that there's something not happening that's correct. Somebody's not overlooking it correctly. So what they're going to do is say, listen, let's grab some coffee and let's weigh it. Okay. And if we can reject the null hypothesis that the mean is at least mu zero, that means we have a problem on our hands and we better fix it. Okay. So it's a left-tailed test because the company is looking for strong evidence that the bags are underfilled. And also, I want to point out here too that we are assuming that overfilled bags, in this case, while it's not a good thing, are a much smaller problem than underfilled. Because we won't get into trouble with the FDA if we give people too much coffee. Okay, it'll suck away some of our profits, but that's better than getting fined by the FDA and possibly closed down. So that's why we're going to set it up this way. Now, you think that would take care of all the possibilities, but no, we have a third case, which is called a two-tailed test. Okay. And by the way, this is all of them. No matter what test we're looking at, this is it. This is as far as it goes. This is different because we just want to know yes or no, is the mean equal to this constant or not? Okay. So it's called a two-tailed test. And so here's a good example. Suppose that Coca-Cola is concerned that their 2-liter soda bottles are not being filled correctly. If they are underfilled or overfilled, the company wants to take corrective action. In other words, if it's underfilled, they'll get into trouble with the FDA. If it's overfilled, then the bottle could explode in the shelf or something like that. So either one of those is not good. We want to find out right away if there's a problem there. So this type of situation can be tested with a two-tailed test because this will reveal if the alternative will tell us whether we have a problem, meaning that is it equal to the right value or is it not? If it's not, then we can investigate further and find out if it's too low or too high. But the first step is to find out if it's not the right amount, not 2 liters, let's say. All right, so we always start our hypothesis testing procedure with these two hypotheses, null and alternative, and they will be determined by the problem itself. This is not something you have to guess at. It has to tell you in the problem what we're trying to find out. Okay. And after, like I said, I mean, after a couple of these, you'll be fine. It's very rare, unless the problem is very poorly written. It's rare that it's so confusing that you can't possibly figure out what they mean. It should be pretty self-explanatory. Okay. Oh, here's one. A major West Coast city hospital provides one of the most comprehensive emergency medical services in the world, operating in a multiple hospital system with 20 mobile units. The goal is to respond to medical emergencies with a mean time of 12 or less. So they want to know if the emergency times are being achieved. You know, they're bragging about 12 minutes or less. So that means that more than 12 would be a problem. And therefore, it's going to be a right-tailed test. Okay. So in other words, the problem would be too high, more than 12, which would mean their bragging is incorrect. So therefore, this one is a right-tailed test. And that, of course, means that they have evidence enough that they can go ahead and maybe make some corrections. Okay, now this refers to the idea that when we conduct a hypothesis test, it's possible that we goof and come to the wrong conclusion. So they've got a nice little table here that I'd like to go over with you. So here's now this is that same test, but oh, all right, let's move it down here. So there's really only th four things that can happen. If our null is true, emergency medical services are meeting their goals, and we do not reject that null hypothesis, then we have the correct conclusion. Fine. But if we goofed it up and it turns out that we rejected it when it was really true, this is known in statistics as a type 1 error. I don't know why. It just is. All right. And, these names are kind of arbitrary, as you can see. So, in other words, incorrectly rejecting the null is a type 1 error. On the other hand, on this side of the fence, if our null is actually false, in other words, the mean time is not below 12, and we reject our null, that means we made the right decision. But if instead we did not reject the null, that means we made a mistake known as a type 2 error. So in other words, this is the case where we fail to reject a false hypothesis is a type 2 error. All right. Now, later on, we'll see more about these, but for now, it's enough to try to remember these. Some things you just have to remember. This is one of them. Type 1, we reject the null when we shouldn't have. Type 2 is we fail to reject when we should have. Okay, so if you get confused, just look at this chart and you'll be able to see what's going on. Okay, we'll see this all the time, by the way. It's not like some not very important concept. We will need these on a regular basis. All right, now, what other things do we need to know? P-value. Now, the p-value is actually short for probability value. So the p-value is actually one approach to testing hypotheses. Okay. So you could think of it as the probability approximately that the null hypothesis is true. Okay, we'll see how to calculate it later on. It's not that difficult. So because of the way it's defined, a low p-value typically it's set at 5%, but it could be lower, indicates that we will reject the null hypothesis and accept the alternative in its place. Because, I mean, imagine if I told, it says, the probability that the null is true. If that probability is 0.01, well, that makes it hard to imagine that the null is actually true. So we reject it because the p-value is so low. We'll use this approach quite a bit. Um, So, like here's a sort of an approximate chart for this. Less than 0.01, if the p-value is that low, then um, we can assume that, something wrong here. Oh, we'll get back to this, but the other approach besides the p-value, I think there's something wrong with this table. I'll get back to you about this. Um, Normally a low p-value means we reject the null, and so I think they got it backwards here. Um, but anyway, let's jump on to here now. So the two basic approaches that we're going to look at are the p-value approach and the one that's sometimes called the test statistic critical value approach. That's the one that we're going to start out with. The p-value approach is a little bit newer, and one of the reasons why it's as popular as it is because often when you use a calculator to get your results or Excel, it'll often produce a p-value for you to make things a lot simpler. Okay. The test statistic critical value approach is a more standardized, more old guard, I guess, approach, which was always a very popular approach. But with the advent of more powerful computers, more powerful calculators, the p-value became more and more popular because if the computer is giving you that number, it means a little bit less work for you. Okay, so um, now they're going to gather this stuff, all this stuff together. And so we can see that it is a procedure that follows these steps. Um, so what they've done is the first three steps do not depend on whether you're using the p-value approach or the critical value approach, as they're going to call it. So we'll look at them both together. So the first thing we do in each case is, of course, the null and the alternative hypothesis. Let me just put this title here real fast. Steps in the hypothesis testing process. Well, we always start with the null and the alternative hypotheses. Okay, that is part of the problem. You have to be, or they have to give you the information so that you can tell what we're trying to test. All right, that has to be part of it. You can't be left guessing. Now, number two, you're going to specify something called the level of significance. And we're going to designate that with the Greek letter alpha. And this formally is equal to the probability of committing a type 1 error. Okay, now you'll see as we go along in virtually every case, we're only really going to choose one of three levels of significance. And so we're going to typically have 5%, 1%, 5%, or 10%. we're not going to see any of the others. There's no reason for it. These are the standard ones. That has to be given to you in the problem. This is not something that you will choose when you do one of these problems. It has to say in the problem, use the level of significance of X, okay? So once that's done, the third step, well, of course, is to gather the data and then compute the value of the so-called test statistic. All right, we haven't really talked about that just yet. From the problem, that is, and use it to determine the value of the test statistic. Now, this is a formula basically that is determined by what kind of problem you're working on. So in other words, it's not really something that you don't choose it. It's implied by the problem itself. So once you've chosen it, then all you really have to do is plug in all the appropriate numbers and you'll have your test statistic. Now, for the p-value approach, the next two steps depend on which approach you're taking, as you saw. Very simply, if the p-value is less than alpha, the level of significance, we reject the null. And if we reject the null, that means we automatically accept the alternative. Otherwise, reject the null. So if you notice, we never use the phrase accept the null hypothesis. It's not accurate. What we are doing is saying we did not reject it, which is not quite the same thing. It's kind of like the difference between being guilty, not guilty and innocent, okay? Because not guilty just means there's not enough evidence to show that you're guilty. Innocent means you really haven't done whatever it is you were accused of. So the p-value that we come up with for a problem, if it's less than our level of significance, remember, the one that has to be either 0.01 or 0.05 or 0.10, if the p-value is lower than that, we can reject the null. Yeah, and it says it right there. So that means that this slide is definitely wrong because you see how we see this is what I was concerned about. If the alpha is less than p-value is less than 0.01, that's overwhelming evidence. Oh, I just realized I misread what they were saying. They're doing this in terms of the alternative hypothesis. That means it's fine. I didn't look closely enough. If this was a statement about the null, then we'd be in trouble. But it's kind of strange the way they've written it here. More than often than not, you would have said instead that the null is false in all these three cases. But all right, this is what they decided to do. All right. Okay. I didn't even realize that they were talking about HA, which is very strange. Normally it's all explained in terms of the null hypothesis, but a very small p-value then tells us that we should reject the null. That's the bottom line. A very high p-value means we should not. All right. Now everything's okay. But let's say we're not using the p-value. Instead, we're using the traditional classic test statistic critical value approach, although they're calling it the critical value approach. It's the same thing. Once we get past the first three stages, gathered up all of our data, we're going to construct a test statistic. And we also need the critical value. Explain when we get to the next problem. And then, yeah. Based on the relationship between the test statistic and the critical value, determine if the null should be rejected. So again, we'll see how that works when we get to some actual examples. Right now, I'm sure it's seeming very abstract. It won't stay like that very long. In fact, speak of the devil, here's an example right here. FTC wants to check Hilltop's claim, or the FTC wants to check Hilltop's claim that its large can of coffee contains 3 pounds of coffee. The FTC director wants to perform a hypothesis test with a 0.01 level of significance to check the claim. All right, so we know that the assumption is that it's 3 pounds. It should be pretty clear that they're only going to be in trouble if the mean is less than 3 pounds. So the null and the alternative will be written in the following way. Less than 3 is the problem area. And up here, the rest is collectively referred to as a right tail. I mean, this is a left tail test. And that's because we're looking for hard evidence that the cans are underfilled. If they are, the FTC might take some action against them. Okay. All right, so we get that out of the way. Now they're telling us right in the problem what the level of significance is. That's this 0.01 here. So this is my level of significance. That is given to you in the problem. This is not something you have to choose. Now, we also have to keep track of the data there. Before we go any further, the data they're giving us is that we picked a random sample of 36 cans. And the mean we found was, only 2.92 pounds. That doesn't sound promising, does it? No, it doesn't. So what do we do now? All right, that's going to, and they also are giving us a standard deviation. Population standard deviation. You can tell, but because we're using a Greek letter there. So this is what we have. Now, the test statistic is what comes next. Now, it looks like they just sort of sneaked that in there. I don't remember them showing it to us. What happened? Oh, it just sort of fell out of the sky. All right, let me show you what this is all about. This is what I'm referring to down here, by the way, right here. This is the test statistic, but the thing is, they didn't really do a good job of introducing it to us. What we need to know is this. When testing hypotheses about the mean, there's only two possible test statistics. The two possible test statistics are if the population standard deviation is known, then we're going to use the following. So you recognize all of these. This is the hypothesized. Of course, everyone recognizes this is sample mean. Standard deviation. And this is the sample size. We know that. Now, if sigma is unknown, instead we use the t distribution, and the test statistic is similar, but not identical. The only real difference is that we replace sigma with s. The one that is consistent with the data that we have. Now here, because the problem gives us sigma, they are using the correct one. But like I said, I didn't see anywhere where they gave it to us. So part is done. This part is done. So the test statistic we choose will be oh, I'm sorry. Wait a minute. My fault. No, they gave us sigma. I just realized as I was writing that it's this one instead. It's the one based in the standard normal. Let's get that out of there. Okay, then we fill in the numbers that they gave us. X bar was 2.92, remember? And The hypothesized mean is 3. Sigma is given us as 0.18. And the sample size was 36. So whatever this number is our test statistic. And you can pop that into the calculator. It's approximately negative 2.67. Now, what do we compare that with? Well, here at this point, we can do one of two things. We can go in two different directions. We can use the p-value, or we can compare it with so-called critical value. Let's see what the p-value approach is all about. So now remember, this is the standard normal, which means, well, of course, we call it or use a z to represent it. The mean is 0, and the standard deviation is 1. And they've given us a value of a test statistic of negative 2.67. So the p-value is basically anything that's more extreme than the test statistic, which means the area under this curve is the p-value. Essentially refers to the probability of being that far out in the left tail when the null is true, the null hypothesis. That I can find out by going to my calculator and calculating this probability. All right, remember we did this yesterday. Second vars. Number 2 is normal CDF. Okay. And then, of course, remember from yesterday, we have lower and upper. Negative infinity. Clean that up. Upper is negative 2.67. And don't forget, this one is replaced with negative second comma 99. So since it doesn't have a infinity button, you replace it with what you saw there, negative second comma 99. And then we have the mean and the standard deviation. 0, 1, because this is the standard normal distribution. And then it's pretty low, but it's 0.00379. That is our p-value. Okay. Now, as far as testing it goes, remember the way this thing works is you're comparing it with alpha. I guess, no, actually, I guess that should be just strictly less than. Now, in this case, remember, they told us right up front that alpha is 0.05, I think. No, zero point zero 0.01. Okay. Our p-value is 0.00379, and that means we're looking pretty good. So then we can decide that we reject the null um, way back here somewhere. We had a null hypothesis. Was this it? Yes. So this tells me that I reject the null, that the mean is greater than or equal to 3, and accept the alternative that it is less than 3, which is bad news for the coffee company because remember, this is their coffee can. They were told by the FTC that if their cans do not contain at least 3 pounds, the company is going to be in a lot of trouble. Okay. All right. Well, now I can't find one, but it originally told us that they were concerned that the cans were underfilled. So by rejecting the null, accept the alternative that the mean is less than 3. All right. So that was a pretty good example, I think. Covered a lot of the techniques that we need to know. That is your classic example, but I would like to point out, though, that we follow the p-value approach here, which in this day and age, apparently, it's becoming more and more common to see it compared to the other alternative approach, the test statistic and critical value approach. So, but we should be comfortable with both of them. So we can't neglect it, even though we get the p-value, and calculators will often provide it to us. We should be comfortable with both approaches. They're going to get to this in a few minutes anyway, but let me show you how that would have worked. This depends on whether it's a left, right, or two-tailed test. And also, don't forget, we are using the standard normal in this case because we know sigma. So then the critical value also has to be based on that z. So z alpha means the cutoff point between the upper alpha percent of the total, and here we have all the rest. Okay. Left-tailed test is based on negative z alpha. So due to the symmetry of this distribution, the area above positive z alpha must be the same as the area below negative z alpha. So this area is alpha, and this is 1 minus alpha. That becomes our critical value. And of course, if it's a two-tailed test, we have to do something a little different. We're going to put half of the area in either tail. So there are two critical values. Positive and negative. This contains half the alpha, this contains the other half. All right, so the logic here is that if the test statistic falls within the shaded region, which is formerly known as the rejection region, there's a reason for that, as you'll see in a second. We reject the null hypothesis. We accept the alternative hypothesis. Otherwise, we do not reject the null hypothesis. Okay, let me make that bigger. Now, the question then becomes, where do I get these critical values? Knowing how they're set up is not the same thing as knowing what they actually are. So for this, we're going to use a function that we used last night, which is INV norm. So for example, given that they told us that the alpha was 0.01, okay. So again, for a right-tailed test, this is what we're looking for. We need a value such that 1% of the distribution is in the right tail and the rest is in the left. And how we do that is with INV norm. on the calculator. If you go to second vars, that would be number 3. And we saw some of this yesterday. And remember, this asks us for the area of interest. Standard deviation. These are 0 and 1 because this is the standard normal distribution. Now remember too, the area is the area in the left tail, which means based on this diagram, 99%. So if you plug those in, you'll get 0.326. Okay. So that means cutoff point between the lower 99% and the upper 1% is right there. 2.326, which can be interpreted as 2.326 standard deviations above the mean. Let me write that in there. All right. So what this is saying, anything outside here, this is what we're going to call our rejection region. Our test statistic is in this region because it's so large. And we reject the null hypothesis and accept the alternative. All right. So that's the cutoff point between rejecting and not rejecting. And our value up here is, where is it? Negative 267. Oh, wait, sorry, that's the wrong one. Oh, no, that was a left tail test. That's why. Okay. So if we had a right tail test, this is what it would have looked like. Okay, that, hypothetically, with a left tail test, we'd be looking at the other tail, the one that has 1% below it. So the left tail test, you're just looking at the other side, and due to the symmetry, it's going to be the same number, just with a different sign. Okay. So 0.01 would refer to the left tail. Once again, we look it up on the calculator. Get this out of the way. So again, with the left tail test, the critical value that we check against our test statistic is we can find it with INV norm, but we technically don't need to because we understand the property of symmetry. But this time the area is 0.01 instead of 0.99. See that it's just the same thing, only negative, negative 2.326. That's again because of the symmetry of this distribution about the mean. And then when we have a two-tailed test, the alpha that we were given is actually equally divided between the upper and the lower tails. So in our case, alpha is 0.01, half of that is 0.005. Actually, let me do this. And that refers to the tail area. Down here at the opposite side. So what are these numbers? Well, how do we look them up? Well, it's a little bit confusing. Tell you what I mean. The area, if you're looking for this one, the area is actually everything below that, all the way down to negative infinity. So that means your area is 0.995. Okay. And the, of course, the mean and standard deviation are still 0 and 1. So if you went into your calculator, you'd see that this is equal to about, it's approximately 2.576. And of course, then you come up here and you'll see that that means if this is 2.576, this must be negative 2.576 because of the symmetry. We don't have to look it up a second time. Okay? Negative and positive. It's the same number. And again, if the test statistic is outside that range, greater than 2.576 or less than negative 2.576, we would reject the null hypothesis. Otherwise, we don't. Now, you may already have made up your mind which approach you like better, p-value or test statistic critical value, but they're both good methods. It's just that in a lot of cases in this day and age, if you've got a calculator, if you've got Excel, it'll often give you the p-value, so that makes things a little bit quicker. A lot of people will tell you this is the p-value is the modern approach. however you want to look at it. They both mean the same thing. There's nothing, they're both completely, one is derived from the other, basically. So it's just a question of picking the one that makes the most sense to you. But if you're doing a mind tap problem, they'll probably ask you to do both. Or they might ask you for critical values, test statistics, p-values, and then a conclusion of some kind. Okay. All right. So God, that was a long example. Let me go back and see if I didn't miss something. The coffee example, and we found, well, first we remind ourselves that this is how a test is set up. We have to have the null and the alternative. We have the level of significance. The test statistic depends on the problem. But I mentioned down here somewhere, yeah, the test statistic of sigma is known is based on the standard normal. If not, it's based on the t distribution. Uh, we've already seen how the test statistic it will depend on the data that we were given. It's the way we calculate is slightly different. So there's our test statistic. Then we compare it to the critical values, which think of them as our benchmark. So here with the p-value approach, we figured it out. The p-value, yeah, 0.00379, which is smaller than alpha, which means we reject the null. If we test statistical approach, we have to find the critical value based on whether it's a left, right, or two-tailed test. And in this case, it's a left-tailed test. So in other words, this is the one, the second one, is one we would use to test this hypothesis. All right, let's do that right now. Well, we already know what the correct answer is. We know that we were able to reject the null, but let's show how that works with the test statistic and critical value approach. So again, the test statistic way back here turned out to be where is it? So we haven't done it yet. All right, let's do that right now. Oh, wait, actually, no, didn't we do this before and find it to be negative 267? That's right. We'll fill it in one more time. It was so far up, I couldn't find it. X bar is, yeah, it was negative 267. That's fine. 2.92. It's 3, the hypothesized value of the coffee cans. Sigma was given to us as 0.18. Then we divide by radical 6. It was approximately negative 2.67. And because we're running this as a left-hand test, we have our critical value in the left tail. That's what the name refers to. And that turned out to be negative 2.326. This is my rejection region. Guess what? The test statistic is way out here somewhere. And that means the test statistic is in the rejection region. And that can only mean one thing, which is reject the null. All right, remember the null was that the mean was at least 3 pounds, which is fine, would have been fine if it was true. Let me go, yeah, there it is. And so we reject the null because the test statistic is in that rejection region. But remember, we also rejected it because our p-value was less than alpha. All right, so if you remember, our p-value is approximately the probability that the null is true somewhere. Point, I believe it was 0038. Let's confirm that. There it is. 00379. That's fine. Alpha is 0.01. Check the null hypothesis. Accept the alternative. So if you notice, both methods agreed with each other. They both rejected the null hypothesis. It turns out that these two approaches, because they're related to each other, since the critical value approach and the p-value approach are related to each other, they must both agree with each other. And that doesn't mean just most of the time, for every single case. Okay? So again, it's just kind of up to us to decide which one to do. So that in a nutshell is hypothesis testing for the population mean. So we know how to set it up. We've got the null and the alternative hypotheses. The alternative is the one that we have to pay extra close attention to because it tells us what we're looking for. Alpha is given to us in the problem. We need the test statistic no matter what approach we're using. Then we can decide p-value or critical value approach. P-value is easy because once you calculate it, you can compare it to alpha and make a decision. P-value less than or equal to alpha, we reject. Otherwise, we don't. The other option is to take the so-called test statistic and compare it to a critical value and make a decision based on that. Yeah, so we see what they're showing here is why both approaches have to give you the same answer, because a sample mean of 292 is the same thing as a p-value of 0038 or a z-score of negative 267. They have to be consistent with each other. In other words, they're so far below the mean that we have to reject the null. Okay. All right. So, yeah, this is what we did before. So, there we go. That's the test statistic critical value approach. This one was the p-value approach. All right, here's another example. Max Flight. They produce golf balls with a mean driving distance of 295 yards. The quality control program involves taking periodic samples of 50 golf balls to monitor the manufacturing process. Now, here, you're going to assume that the mean of the golf balls is 295 yards. Anything else will lead to them being manufactured differently. Although they didn't really explain that particularly well, I thought, but still, that's what they want. And that means that this is a two-tailed test. Okay, because we're trying to show, yes, they have a mean of 295. No, they don't. That would be a classic example of a two-tailed test. All right. So what else do we know? The mean driving distance for these golf balls is 295. There we go. So we're basically being asked to test if this is still true. Okay, so we've got the mean, or the hypothesized value of the mean is 295. Historically, I guess they've had a mean of 295. We want to make sure if that's still the case or not. We take a sample of 50 balls, and it says here that if the mean is 295, that's fine. Otherwise, we'll adjust the process. So we know that this is a two-tailed test. Then they have to give us the level of significance to test everything at, which is, you see right here, it's 5%. And then we can look up or calculate the test statistic. And because, oh, I forgot to write down the data that they gave us, or at least not all, I didn't get all of it. Somewhere in here they mentioned the standard deviation. Oh, there it is. The sample mean from these golf balls is 297.6. And they're telling us, they're trying to be careful here to make sure we're aware that this refers to the population standard deviation. It's 12. So once again, we're going to use the standard normal distribution for a test statistic. And we have all these numbers. The mean is 297.6. The hypothesized value is 295. It's taken from here, the null hypothesis. The standard deviation is 12. Sample size is 50. All right, we pop that into the calculator. I got 1.53. All right, so now I'm not sure if they want to, which approach they want us to use. If they don't care, they won't tell you which approach to use. Usually they encourage you to do it. Well, it doesn't really matter, but I mean, MindTap might ask you to do one or the other. So, oh no, I guess they want us to do both. Okay, so they're starting us off with the p-value. So remember, this is a two-tailed test. We want to know if the mean is 295 or not. The approach is a little different, by the way, with a two-tailed test. The one we saw before was a left-tailed test. Let me just go back and revisit this. And see, where did we find the p-value? It's just the general setup. Oh, that's right. It's down here. It's 0.00379. Yes. Well, anyway, this is different because it's a two-tailed test. What you have to do here is to find your test statistic. And the negative version value equals the sum of these two shaded regions. We didn't see that before. So we're going to have to go to the calculator. Now we only have to calculate one of these. They're both the same area because of the symmetry of the curve. So what we're going to do is let's just say we'll solve for this one. And then whatever that number is, we'll double it. And that will be our p-value, symmetry of the curve. So we'll have the area, mean and the standard deviation. Oh, wait a minute. No, sorry. I hit the wrong button. That's why I've got the wrong one there. Sorry. It's lower upper and sigma. So the left tail goes down to negative infinity. But remember, this is the same thing as second comma 90. Actually, sorry, it's negative second comma 99. So if you put all those numbers in there, good. Get old numbers in here. All right, that much better. So negative second comma 99, negative 153, 0, and 1. we're looking at 063. And that means this area is 0.063, as is this. Value is the sum of those two. Because it's a two-tailed test, so that's our p-value. Now remember how this decision works. With the p-value, that means reject the null, accept the alternative. Um, Otherwise, do not reject. Now here, the alpha they gave us was 0.05. Well, I think we can see where this is going. So we're not going to reject the null. Okay. Which means that the golf balls have the right distance. The alternative would have been that the mean is different, but that's not the case here. So that means the golf balls are doing exactly what they're supposed to do. Now, they also, it looks like, want us to try the test statistic critical value approach. So we already know the test statistic from up here was 153. Values. Because this is a two-tailed test, we have to cut them in half, or at least the areas in half. And that's my rejection region, right? So alpha is 0.05, so we can find the specific values. And so we just need to calculate one of these. Because one will be the same as the other with a different sign. Now, this is the one where we need I and V norm. Oh, and sorry, that's number 3. And of course, remember, this is the one that just asks for the area, the left area, left tail area, which means 0.025. Mu and sigma. And if you pop that in, you'll see that it is, in fact, uh, it's negative 1.96. And that means the other one is positive 1.96. All right, let me sketch out the diagram. So again, with the two-tailed test, the shaded regions are my rejection region. But remember, my test statistic was here somewhere, 1.53. And guess what? It's not in the rejection region. And so therefore, we do not reject the null. So both approaches again gave us the same result. The p-value told us that the p-value is too high to reject the null. And this approach told us that the test statistic is not in the rejection region, which means do not reject the null. Any way you look at it, we do not reject the null. And therefore, the company does not have to adjust the golf balls. So here, yeah, so this is what the 1260 is their p-value, which is what we got. And you can see in the diagram, they took the area of both shaded regions to do this. And then we did the same thing. And we compare that to alpha. Okay. Then here for the critical value approach, we looked at the critical values, compared them to the test statistic, and looks like they forgot to put it in there. It does not reach the critical value, the rejection region, I mean. Okay. Okay. So a lot of examples. This is good. I like to see lots of examples because that's really the best way to learn this stuff. Although once you start doing the mind tap, it'll give you multiple opportunities to try each one. Now, I see here that they're showing us some spreadsheets here. We are going to do this very soon, maybe not tonight. It's a little late here, but we're going to try some of these examples in Excel as well as on the calculator, okay? I'd rather just save a couple of these and then do it all at once than try to sneak in one or two here or there, but they would like you to know that you can get the same results in Excel if you know what the commands are. So don't you worry, we'll get to this, just not tonight. All right, tonight is a calculator night. Okay. Now they would like you to also see, for how obvious it is, but hypothesis testing is closely related to confidence intervals. So, like here, for example, this is the one with the golf balls. And the way this works is what they've done is they've constructed a confidence interval for the mean flight of the golf balls. And then in that confidence interval turned out to be between 294 and 300.9. Now, the null hypothesis is that this is 295. So the way this works is if you do have this confidence interval, if the hypothesized value is in the confidence interval. Do not reject the null. And that's what happened here. It's in the interval. Now, obviously, that means that if the hypothesized value is not in the interval, then we reject the null and accept the alternative. So if let's say the hypothesized value had been 290 or something, we would have been able to reject the null. Okay. But that didn't happen. And so again, this has to be consistent with the two hypothesis tests that we did, once with the p-value and once with the critical value. They can't disagree with each other. All right. Now, somewhere along the way, I know we got bogged down in a lot of details, very important details, but we're actually, there's a second case that we need to consider. Let me just go back and revisit. I want to find where I wrote down the cases. So here we start out with a general look at hypothesis testing, some of the terminology that we need. Uh, but I did mention that when we're testing here it is. Um, yeah, in other words, when testing hypotheses about the population mean, if the standard deviation is known from the population, we're going to use the standard normal distribution to test the hypothesis. If not, we'll use the t-distribution. Okay, so since then, we've done nothing but use the standard normal. All right, now it's about time that we looked at the t-distribution. Value, sorry, test statistic, and the p-value is the area in the tail there, 00379. Might as well label that here. And that's what gets compared with alpha. The other alternative is use the test statistic critical value approach. And that's when we need to know how to find a critical value. And that depends on whether the alternative is right-tailed, two-tailed, or left-tailed. Once we've established that, we can use INV norm to find the actual values of these critical values. Go ahead and compare the test statistic. If the test statistic is in the shaded region, which is our rejection region, then we reject the null. Otherwise, we don't. Value and the test statistic critical value approach both provide us with the same results. All right, I'm just double checking to see if we left anything behind. No, I think we're good. So let's at least take a peek at the t statistic and what happens differently when we use it. So of course we know that the test statistic has a different, slightly different form. Test statistic, again, it's very similar. And also the critical values, if we use them, are taken from the t-distribution. Let me just quickly run through that with you. It's in a very similar way to what we did with the standard normal. In other words, there's a left tail test, there's a right tail test, and a two-tail test. Remember, n is the sample size, n minus 1 is the degrees of freedom. Okay, degrees of freedom, I've mentioned this a couple of times, is based on the sample size that we're using, but it's different for every application. All right, so when we do something different later in the chapter, don't assume that the degrees of freedom is always the same, because it's usually not. That information to look up these values in your calculator. All right, now the left tail test, you can probably guess where this is going. So that, again, that shaded region is our rejection region. And of course, the two-tailed test means we split the alpha up into two regions. Oh, I just realized I made a mistake here. That should not have been cut in half. I apologize. I just noticed that. Sorry. Yeah, this should no. It's a one-tailed test. So this is unfortunately this is wrong. This should have been just plain alpha. But now down here, um, we do have to cut it in half. Okay, so in other words, other than that, it's exactly the same as what we had with the standard normal distribution. And of course, the test statistic is different. But other than that, we could also use the p-value approach, um, not using INV but INVT in the calculator. Okay. So yes, they're telling us how to do it both ways. So we have all of these, and more Excel. Don't you worry, we'll get to this. And then they're going to save for the end this discussion about the population proportion. We did some of this yesterday when we did those confidence intervals. So that was already chapter 9. My God. So you know what I think we'll do now. Like I said, I don't know. There's in the classroom, I always have a nice break in the middle somewhere. Somehow, once I get rolling on this stuff, it's hard for me to stop. So I did not give you a break, which I should have. And wow. All right, where did we leave off? There we go. This business travel magazine example. What slide is this? This is 44. Okay, so you know what? I was thinking that maybe we could stop right here and carry on. Now, tomorrow, remember, I can't be here, so I'm going to make a recording instead of having a live session. So I'll send out an email and remind you about that. Literally, just all I'm going to do is just wherever I am, I'm going to sit in front of this computer and record the session. I'll post it in Blackboard, and then we'll just take it from here. And then next Monday, everything will be back to normal. We'll meet from 6 to 9, Monday through Thursday. And I don't think there's any other holidays coming up that I'm aware of. So we should be able to just, have normal sessions every night. And before you know it, we'll be done. It's a very short semester, something like 5-6 weeks or something like that. So already we're zooming along here, so I'm sure we'll be done in plenty of time. So anyway, in the meantime, what you can do is sign up for your MindTap or Cengage account, so you can use MindTap and start working on the problems. You can start them anytime you want. They're already open. And the other option is to read through the slides, maybe look at the book. Although, no, sorry, you can't look at the book until you have your MindTap set up. And maybe look at the handwritten notes just to make sure you're keeping up. And so maybe as soon as tomorrow, we'll have some Excel as well. Okay. So, all right. I think we're ready. So I'll see you tomorrow, well, with a recording, and then I'll see you again next Monday. Okay. I'll see you then.
Thank you.
All right. You're welcome.
Thank you.
All right. Good night.